Hey all, I'm Matt, the host of Big Forest Trail Map podcast. On Trail Map, we explore the winding, unconventional paths that people take to build meaningful lives and work. Each episode, I sit down with someone who's forging their own way. Entrepreneurs, chefs, scientists, athletes, and more. To hear about the decisions that shaped them, the challenges they faced, and the unexpected turns along the way. You'll hear stories of grit, reinvention, and resilience, plus some fun, surprising, and amazing moments along the way. Whether you're charting your own course or just love a good story, I hope you'll join me on the journey. Trail Map is part of Big Forest, a business that I started to support people who are on their way to building amazing businesses, careers, and lives. Big Forest offers leadership and professional coaching to anyone dealing with current and unresolved issues in their careers, whether that's feeling disconnected with values and purpose, navigating challenging circumstances and relationships, or trying to build new things. Please visit bigforest.llc to schedule a complimentary 30-minute meet and greet to find out if coaching is right for you. Hey guys, welcome back to episode 3 of Trail Map Podcast. Just want to say thanks for all the support. I've gotten a lot of good positive feedback on the first 2 episodes. Really appreciate all of that, and please keep it coming. If you have a chance to, definitely subscribe, whether you're on YouTube, Spotify, or Apple Podcasts. It would be great to have your support that way. And just reconnect with us. So today I'm joined again by Pat Wolf. It's really nice to have him back after episode 2.
Matt, this is great. I am honored. I'm honored to be back.
Well, it's good to have you, Pat. And it's fun to have these conversations, and it's great to have a reason to reconnect with good friends and to have conversations with interesting people, which I guess leads us right to today. We're chatting with Nathan Howard. So quick bio on Nathan. Nathan Howard is a principal research scientist at MIT's Plasma Science and Fusion Center, where he leads efforts to understand and tame turbulence in fusion plasmas. With a PhD in nuclear science and engineering from MIT, he specializes in using both cutting-edge experiments and supercomputer simulations to improve the predictability and performance of fusion devices. His work has earned prestigious recognition, including the Nuclear Fusion Award, for breakthroughs in modeling how heat and particles move within fusion reactors. On a personal level, Nathan is also a husband and father, a passionate fly fisherman, and an astrophotographer. So as I was reading and writing his bio, I'm like, I didn't know what a lot of these words were before the conversation. I feel like he gave us a good education, so I'm excited to share that.
He did. I mean, I know many of us do tame turbulence in fusion plasmas, but he's leading the efforts. So
no doubt.
Should listen to what he has to say.
He made that clear. He made that really clear. Yeah. So really glad to have had this conversation with Nathan. So I think there are a few reasons why this episode is really worth listening to. As a technology, like fusion is really one of the leading candidates for powering our future. It's potentially a clean, carbon-free energy source, and that's really exciting. I know, you just have to open the newspaper or turn on the TV right now, and there's so much fear and anxiety around climate change and what that's going to do to us. And, we're seeing the impact in terms of like extreme storms and all of that. And so it's felt very hopeful for me to have a conversation with somebody who's really very dedicated to this technology. And I think his biggest motivating driver is helping to work on this climate change issue.
And I don't know about you, Matt. Fusion and fission, not the same thing. Did you know this going in? I did
not. No. Yeah. I mean, just to be honest, I think we got probably 3/4 of the way through the conversation before I was like, oh yeah. Yeah, there's a difference there.
And that's key. Like what he's working on it's not there yet. Like there are nuclear power plants. There have been, like people have heard of like the disasters related to fission.
Mm-hmm.
Right. But this is something different that they're working on.
Correct. And there are, when you hear about, meltdowns, and when you hear about, weapons, nuclear weapons, like you're hearing about fission. And so, Nathan is really one of the leading scientists where it comes to fusion. And they're very much at a place with fusion where they're taking the technology from the lab and looking at how to translate it into kind of utility scale technology. So pretty exciting from that perspective. And it's really cool that we're able to have a scientist like that on the show.
Yeah, big time.
So, quick science lesson here: fusion versus fission. Fission is what powers today's nuclear reactors. It's the process of splitting heavy atoms like uranium to release energy. It works, but it creates radioactive waste and carries some serious safety concerns. Fusion, on the other hand, is what powers the sun. It's the process of fusing light atoms like hydrogen together to create energy, cleaner, safer, and virtually limitless. That's where Nathan comes in. He's part of a team at MIT working to bring fusion power out of the lab and into the real world. Let's get into it. And then I think, and this is probably a bigger portion of like what we're here for at Trail Map, really trying to get to know Nathan as a human too. And, I think one of the reasons that I've enjoyed getting to know Nathan is he's a well-rounded person. He has a bunch of interests outside of fusion, which we get into a bit in this podcast.
He also enjoys fission, but
he also,
no.
yeah. And I think like it's really cool to see somebody who, has had such a kind of an organic discovery of an interest in his career area and what it's like to be on a scientific frontier and kind of just like follow your interests. And I think there's something.
Yeah, it seems, I mean, just from talking to him, it seems like he indeed, like he kind of like followed his heart, or I don't know if you know the joke, Joseph Campbell, his saying was, follow your bliss. And then,
Okay.
Later when people were like, hey man, I followed my bliss. Like, what happened? I'm just strung out. And he's like, oh, I should have said, follow your blisters. Because it's like, working hard at the thing that you enjoy, like that'll lead you to the right place. And I think Nathan is an example of that. Like he's just followed what's been very interesting to him, and that's led to one thing, that's led to another thing, and that's led him to being, as you said, a leading scientist in like this major technological area of research.
Yeah. Yeah. It's, I talk to a lot of people who are like thinking about career transitions or, looking at jobs. And it's just, when you think about it, it's just a very different way of approaching life to, really focus on like your interests versus like, where is somebody else hiring? It's like, Nathan has chosen to really just pursue the things that interest him. And I think that that's blossomed into something where he's highly, highly employable. And I think you could make the argument that like not everybody gets that opportunity, and I think that would be true. But I also think there's something that everybody should try, which is trying their best to go after things that light them up.
There's lots of trails, you can follow the one blaze and that's cool, but sometimes there's the two blazes next to each other and you can,
Yeah,
you can.
totally. Cool. Well, yeah. So I think we should jump into this conversation. And anything else you want to say, Pat, before we jump in?
He was just a really interesting guy. It was good to meet him. I hope I can meet him in person one day and ask him to explain a lot more stuff to me.
Yeah. Yeah. There's a lot for him to teach us.
Yeah,
Cool. All right. Well, we'll get on with the conversation.
let's do it.
Nathan, it's great to have you here today.
Yeah, thanks for having me on.
Well, yeah, I think we can dive right in here. The first thing that everybody wants to know is, what do you do with your time?
As most people, most of my time is spent at work, unfortunately, or at least 8 hours a day, right? So for my day job, I'm a plasma physicist. I do research at MIT. I work in nuclear fusion energy research, and I'm a principal research scientist. So what I do on my day job is essentially research. I advise students and postdocs and trying to develop nuclear fusion as a potential energy source. Outside of that, I like to fly fish. That's one of my big hobbies. I would fish as much as I could possibly do. If someone would pay me to do it, I would definitely assume that as my paid job. But fortunately, I've yet to find that opportunity. I like to do astrophotography and play sports. So those are kind of my overall activities, I'd say.
Awesome. How do you fit that all in?
Well, we have a cabin in New York. I try to do astrophotography when we're on vacation there, and just weeknights and things for sports activities, and I try to fish as much as I can. Yet that there's the Catskills where our cabin is that I tend to go to, do a lot of fishing there. I've also traveled around the world. I've been to New Zealand, Patagonia, Labrador, Seychelles, Mexico, fly fishing around. So I try to do that as much as I can as well. My record is 55 days on the water 1 year.
Wow.
But that hasn't happened in years. That was, I think, 2015. But that's pretty good considering that isn't my job to fly fish. But yeah, it's just a balancing act. It's, try to work hard and play hard, I guess.
Well, yeah, really cool to have you here. You're the first scientist that we've had on the show. And, I think that really interesting to hear a bit more about the world of nuclear energy. And I guess I'm curious, like what drew you to that initially?
I've been interested in science for since I was a kid. I think it was probably sort of as far back as when I would hang out with my dad. We go on hikes and things like that. So it was more like a nature slash science thing. So I really liked that. And then let's see, in terms of for whatever reason, when I was like, I think what was I probably 1994. I was like 11. I got really interested in nuclear weapons. I'm not really sure why. I can't remember why I was interested in that, but I started reading about it, and I was just like, wow, this is super cool. I actually I don't work in nuclear weapons now, and I kind of morally opposed to doing that, honestly. But that's kind of what got me interested in nuclear as a whole. And then I decided I was interested in physics, and ended up thinking I would go to college and study physics. And there's a bit more in the background there. I was originally interested in astrophysics, and then went to college, pursued a physics degree. Happened to be reading a Scientific American article in like somewhere around the 2000s that was on fusion energy, and I said, "Well, that sounds pretty cool. I think I'll try to get an internship in that." So that summer, I applied to internship there, and I did an internship when I was about, I guess, it was after my junior year at college, at General Atomics in San Diego. I was there all summer. I worked on a experimental fusion reactor at General Atomics called D3D, and I said, "Hey, this is really interesting." I pursued it in grad school, and then postdoc, and then all the way to being a research scientist. But that's kind of the rough timeline of my entrance into this field.
It's interesting that your way in was through nuclear weapons and now you have sort of the moral opposition to them. But do you remember what hooked you as you started to learn about nuclear energy?
Yeah, I mean, so the reason I'm interested in fusion and plasma physics and things is really because of the possibility of developing fusion energy. Some people are into it because they're interested in the physics, right? Namely, they're interested in really what are the physical processes that are going on in this controlled experimental reactor. I'm actually interested in this ultimate goal of generating, clean electricity. So that's, I feel strongly about climate change, and trying my best to address that, for future generations. And so really it is that pursuit that really has me interested in working in fusion energy. I mean, I'm very interested in the actual physics as well, but I see it as like, I'm interested in the application of that physics to actually achieving, controlled nuclear fusion, which can lead to production of electricity from fusion energy.
Could you tell us a little bit about what the word turbulence means in the context of what you do? I've seen that word on your website and bio and whatnot.
Yeah, so what happens actually in a fusion reactor, right? You're trying to basically replicate the conditions that are near the center of the sun, actually, hotter than the center of the sun. So this is because, let me go all the way back to describing a little bit about fusion, and then I'll kind of get to answering that question. I apologize for the
So I'm just jumping in the middle here. Sorry.
okay,
No, it's
that's
good. It's good.
we in order to make fusion happen, right, you have to actually have two light atoms. Namely, we use isotopes of hydrogen, so different types of hydrogen. It's called heavier isotopes of hydrogen. So you have deuterium, which is a proton and a neutron in the nucleus, and you have tritium, which is a proton and two neutrons. And so a normal hydrogen atom is just a proton with an electron around it. So its nucleus is just one proton with an electron around it. We use isotopes of hydrogen, so deuterium and tritium, and we try to actually get them energetic enough so they have a collision. And with those particular atoms, if you run together with enough energy, there is a finite probability that they will actually fuse together, and they fuse together into a helium nucleus, and they release a neutron that is very energetic. So it ends up that the original atoms have more mass than the product, and so they release the difference in the mass in the form of energy. And so that gives you this release of energy that you can then harness to actually, eventually make electricity and things like that. So in order to do this, the chances, so if you have an atom, typically it's neutral, right? It has an electron around it and a proton at the center for a hydrogen. And so if you heat that atom up enough, you'll enter a state that is called a plasma state. And so what happens is you put enough energy into the system, your electron becomes free. And so you have a free electron floating around in this free ion. So one's positively charged, the ion's positively charged, the electron's negatively charged. And if you do this, if you have a lot of these together, it's called a plasma. It's like the ions are free floating around, the electrons are free floating around. And this is actually a really, it seems like an uncommon state of matter, right? It's the fourth state of matter. You have, solids, liquids, gas, and then if you put more energy into it, you can achieve these plasma state. And it's actually the most common state of matter in the universe. About 99% of the known universe is made of plasma, because every star is just a giant ball of plasma, basically. And so when you have this really hot plasma and you have these free ions floating around, there is some probability that two of them run together and they fuse together and release energy. And this is essentially the way the sun works. But the probability that those two positively charged nuclei run together and they collide off of each other, because they're both positively charged, so they want to basically bounce off of each other. That probability is way higher than the probability that they actually fuse together and release fusion energy. And so essentially you have to create a situation where these free nuclei have a large number of opportunities to run into each other, because every once in a while they'll actually fuse together and release energy.
Make it crowded in there?
Sorry, what'd you say?
Make it crowded in there?
Exactly. So one thing is you want them to be really hot, so they have a lot of energy, and you want to have high density, right? So you want it to be very crowded, meaning there's lots of opportunities for these free nuclei to.
How hot are we talking? You're saying hotter than the sun?
Yeah. So the peak of the cross section, which means the place where you're most likely to create fusion with a deuterium and a tritium atom, is actually around 15 keV, which is roughly something like 150 million degrees Celsius. And so I think the melting point for like most materials, the highest melting point for a solid material is something like 3,000 degrees Celsius. So you're way hotter than anything that you can't contain this plasma with a solid container, because it will melt, basically.
So it's similar to when I went to a day game at Yankee Stadium and I was trying to sit on the seat.
Yeah.
That was like almost a plasma. Yeah, okay.
Yeah, it's similar feeling, I'm sure, but but so in order to do that, you actually can't use a metal container to contain this plasma. So what you end up doing is use a magnetic field. Because the plasma is made up of positive and negatively charged particles, those particles will stay confined to to a magnetic field line. So you can create a bottle, right? And think of a bottle that's shaped like a donut, and so that has no ends, right? And so if you think about it, the particles will spiral around those magnetic field lines that are shaped like a bottle, and you can kind of keep the plasma contained.
Is this every reactor what you're describing in terms of that type of setup?
No, so this is a particular type of reactor called a tokamak that I'm really describing. So I work on tokamak fusion reactors. They're a type of magnetic confinement.
How big a donut are we talking about?
So the size of the donut is related to how well it contains the plasma. So the one that I worked on for my thesis, which used to be at MIT, was think like a Chuck E. Cheese tube, right? Like it was like the size that you crawl around in one of those tubes at Chuck E. Cheese. It was about that size, but
pretty small.
This was a compact reactor. Yeah, it was a very small one. I could not personally fit inside of it. There were grad students who would go inside the reactor, but the port was about like, I don't know, like 10 inches, so you had to squeeze through it to get in, and I had no desire to attempt to fit through that.
Claustrophobia is being triggered right now.
Yeah, mine was too. So I was like, yeah, I'm good. I'm never gonna go with that thing. So like, send someone else in there.
It's safe for you. Just did you put the grad students you didn't like in the donut, or
I
it's
mean, it's
safe
already
for
crowded.
people to
It's
go
crowded
into?
in there. We established.
Well, there's no plasma in there when you go in,
Okay.
right? So
Okay.
in order to make a plasma, you actually so just to step back to the one I worked on was called a compact reactor. So it was very small. The larger one, the one in San Diego, D3D, is so large that you can walk around in it. Like maybe you have to duck down a little bit, but like it's quite large. And then there was a very large one that just shut down in the UK called Jet, which was extremely large, right? Just to give you an idea, so the distance from the so if you imagine a donut, right, the distance from the very center of the donut to halfway across the donut it was about almost I think it was almost 3 meters. Particular fusion reactor was so we worked on a small one. Just for context, the one that is being built that I work on in Devens, Massachusetts by Commonwealth Fusion Systems is the same size as the one in San Diego, which is sort of large enough for you to walk around in, crouch down. So it's a bigger reactor than the one that I worked on.
So
But
Nathan, are all of these reactors that you're describing intended for R&D purposes? Is there a plan that they would could be used for actually scaling energy output?
yeah, so right now, all these are research reactors. There have recently become plans within the US fusion program, the world fusion programs, and by private companies to develop something called a fusion pilot plant, which is basically it's kind of a first of a kind of a power producing reactor, right? So it's right now no one has created electricity from their fusion reactor. So we just generate the plasmas, we study them, and then we try to say if we had tried to produce electricity from this, we would get X amount of megawatts out. That's kind of that's the closest we've come so far. But there are plans in place from in the US and Europe and from private companies. The one that I'm most familiar with is Commonwealth Fusion Systems to build electrical producing reactors. In fact, Commonwealth Fusion Systems is designing one called the arc reactor, which if you're familiar with Iron Man is also the name of his little reactor that he built, and that one is supposed to be built in I think Chesterfield County, Virginia, and come online in the 2030s. And it should produce something like 420 megawatts of electricity. Yeah, so right now most of the things are research reactors, but there are plans in place to scale them up to basically electricity production.
Do you know what problem needs to be solved for this to scale and for it to be efficient, or is the exact problem unknown?
Yeah, so there have been numerous sort of reports that have been put out in the last even like in the last 5 or 6 years from the community that basically outline what are called the gaps. So what do we have to do to get from where we are now to like a power producing reactor? There are a number of gaps in different areas. The plasma physics gap, which is the one I actually work on, really, which is how to create the conditions in your plasma that will give you the most fusion out, is actually one that's a bit more advanced than some of the other areas. Meaning we think we have a reasonable idea of how we can make a plasma that will give you positive electricity production. That is not, there's still a lot of research going on, and we have models that we think are pretty accurate for predicting that. So that is probably not the largest gap for creating a fusion reactor, but there's still a lot of work there. The largest gaps are actually related to something like materials. Even though you have this magnetic bottle, sometimes the products of the fusion reactions are really energetic neutrons and things, and they can run into material surfaces and they can make them brittle over a large period of time, right? So we've never had to deal with a problem where we create so much fusion over a long period of time that we have to worry about the material properties over 20 years, right? But when you build a power plant, you have to actually know that your structural material is not going to degrade over 20 years, right? And so a lot of those materials type issues are really understudied, I would say. They're kind of the largest remaining gaps. There's another gap that really has to do with power handling. So when you put a bunch of power into the reactor to get it hot, and then it becomes really hot, it creates a lot of fusion, and then it actually pretty much self-heats, right? So it's creating so much fusion that it's actually heating itself. So what happens is some of the products of the fusion reactions stay confined, and they they help continue to keep the plasma hot. So you can sort of turn off your auxiliary heating. And when you do that, though, I mean, when you reach conditions where you're really producing a ton of power, the problem is it slowly diffuses out. If you think of it this way, it slowly diffuses out of your reactor. And actually, I never answered your question on turbulence. I'm very slowly getting
We're
there.
getting there. We're getting there.
So the problem is the very core of your reactor, you want to be like 150 million degrees Celsius. The very edge of your reactor, you want to be room temperature because you don't want to melt your wall, right?
Sure.
And so the problem with that is you have a huge gradient then, right? Like 150 million here, and then a meter and a half away, you have like, you want to have 72 degrees or something like that. But
It seems like the radiant heat would just be impossible to contain. I mean, I'm sure there's the conditions that can be, but that sounds crazy.
so this is where turbulence really comes in. Like, because you have this huge gradient, you have a source of energy in your system which can actually drive turbulence. And so turbulence, if you think of it, is like basically the generation of these large scale structures like eddies and things like you might think of from fluid turbulence that can move heat from the very center. They can move heat and particles from the very center of the plasma to the edge very rapidly. And so what that means is that you put power in the core, or you put heat in the core, and it really rapidly moves to the edge of the plasma, right? And so that's bad because you're losing energy and heat from your system, and so it's cooling down faster than you'd want it to. And so what I study is the sort of physical processes that cause the turbulence that we observe and I simulate that turbulence to try to understand, can we predict the heat losses from our plasma, and can we optimize them to give us better performance, right? So basically, when we put power in the middle, can we get it to stay there longer so it stays hotter for longer? But the ultimate problem is it's unavoidable that you can never minimize those to zero. You're always going to have some heat and power flow from the core to the edge.
And I guess one thing, to take a step back, one thing that I've noticed, like being in Boston around big universities, is there's so many amazing scientists that are in this community, but many, if not all of them, work on very small slices of big issues. And so I'm just wondering, like, where with an issue like nuclear energy, nuclear science, where we probably want to get to the outcome as quickly as possible from like an existential, like climate change perspective, like who's coordinating these efforts? Like who's helping to map the gaps and think about the allocation of resources? And to what extent, as a scientist working on this, are you thinking about the big picture?
Yeah, I mean, you're absolutely right. I think, most scientists, tend to be very like hyper focused on their one thing, right? And this can be a problem, right? I mean, it's a problem in a lot of ways, right? Is when you're super focused, even, in your narrow scientific area, you can't even identify what are the big picture questions you're trying to answer, right? But even more than that, in this context where you're trying to actually ultimately create a working fusion reactor, right? Like, it's always good to try to be able to put what you're doing in the context of how are we going to make this whole device work. And so to answer your question, there have been community workshops that have gone on where we've gotten together everyone from different areas. People who do fusion materials, people who do heating systems, people who do power handling, people who do core plasma physics, things like this. They've all gotten together. We spent about 15 months going through about three different national meetings in 2019 and early 2020. I was actually one of the co-chairs of that process, and we put together a report that then fed into another committee, essentially, who put together the final report, which is about a 200-page document that says, here is how we think we can get from where we are now to a power producing fusion reactor. And so from the public side, it is the Department of Energy who is actually taking the output of those reports and formulating the U.S. fusion program to best, reflect the things that were in those reports. So they say, well, our biggest gaps are in fusion materials and technology, so we're going to probably allocate more resources in that direction, right? And they've done a good bit of that since these sort of community reports came out. On the flip side, because we have a fusion industry, those companies are a little bit unique, right? Like Commonwealth Fusion Systems has people who are thinking about because their goal is to literally create a power producing reactor, right? So a power plant. And And because of that, they actually have people who are thinking about the blanket technology, the material technology, the magnets, the plasma physics. They have people in each area, and as a company, they can't just be narrow-minded, right? Because they have to put together the whole picture. And so that's kind of been an interesting evolution in the last 5 or 7 years. Is that some of these very legitimate private fusion companies have come about who have entire teams of people who are not always from plasma physics, but came from other engineering disciplines, to start thinking about some of these problems that we kind of know we have to solve, but have traditionally been not as well investigated as other areas.
Maybe some of the problems, like you were saying, that the sort of downstream commercial problems, like in terms of scaling this, haven't been as focused on in the research environment. I could imagine in a commercial environment, that would be a much higher priority.
Yeah, exactly.
It strikes me that you're a scientist who's involved in the details, but who's also thinking about the big picture and the important. You've even said that that's a huge motivator for you. So, how are you feeling? What is your level of optimism around the technology, and what impact do you think it will have on the planet?
Yeah, so I mean, I'm pretty optimistic at the moment, right? I think, and again, I keep referring to CFS, which is Commonwealth Fusion System, because I do some research contracts for them to do some research on their proposed reactors, and so I think they personally have a very realistic plan for achieving fusion, and there's other approaches that are going on around the world that are kind of trying to accelerate the timeline to getting to fusion energy. And so right now, I think we've made a ton of progress on models. So one things I actually do performance projection. So I use these turbulence models to project the heat losses in tokamaks. And when I do that, I can then predict what the profiles, like how hot and how dense they should get, which then I can then predict how much performance they should have, right? So how many megawatts of fusion energy will they generate, or fusion power will they generate? And I think our models have gotten to the point where I have a pretty high level of confidence in them. They still have significant uncertainties and we have to make assumptions, but what I've told people, for instance, with in 2027, Spark is supposed to get, a Q greater than 1 in this device that Commonwealth Fusion System is building. And what I've told people is if Spark is built up to spec from the engineering side, right? Like and that's not something I'm personally involved with, but from the physics side, if Spark can't get Q greater than 1, then I will probably look for a different career, because I'm confident enough that we understand the physics to the point where it will get Q greater than 1 if everything works from sort of the engineering side, right? And so I'm pretty optimistic that we're very close to a situation where there's going to be tokamaks coming online that are generating more power out than in. And this will allow us to basically, for the first time, say that fusion energy, quotation marks, works, right? Like, because I kind of think this is like a Kitty Hawk type of moment, right? So you've finally taken off, right? And until you've done that, I think people always have this joke of fusion's going to be 20 years away and always will be, right? Like that's the traditional joke about fusion. But when you really show that you're getting more power out than in, and you're kind of showing this is close to taking off. And so I'm pretty confident that the amount of investment into pushing it forward beyond there will kind of increase, and that will actually be able to go to the next step where we create fusion electricity, right? Electricity from that. So I'm personally pretty optimistic at the moment that we're something like 10 years away from having potentially electrical production from a fusion reactor. And what will that mean for the world as a whole? I mean, I think there's always going to be a need for energy mix, right? But fusion energy, if it could actually create electricity, it provides a means of clean baseload electricity. Baseload meaning that it's you can turn it on whenever you want, turn it off whenever compared to things like solar and wind, which are more dependent on the sun and the wind blowing, right? So sort of a baseload electricity that is carbon free. Relatively, it doesn't have a lot of the safety issues that are generally associated with nuclear fission, which is your traditional nuclear power plants. I'm pretty optimistic that on maybe the 15 to 20-year time scale, that fusion could potentially be adopted worldwide and be a really big part of the sort of clean energy mix, I think.
Can I ask sort of like and you kind of just addressed it there, yeah, sort of the inverse of Matt's question, which is like, is there anything about the potential safety that gives you pause? Like at the beginning, you were talking about, you're dealing with the temperatures of the sun and that the materials can degrade. Does that give you any concern? It seems like it could get out of hand, but I don't know. I'm
Yeah.
not I'm not in the tokamak every day, so I don't know.
Yeah, I mean, that's a great question. I mean, so when people talk about, the thing that everyone's aware of with like a traditional nuclear reactor, which is based on nuclear fission, is sort of the meltdown scenario, right? We've all heard of that, right? With a fusion reactor, even if you had a sort of worst case scenario where you have a plasma, it's creating a lot of fusion, and somehow you kind of lost control of it. In fact, sometimes this actually does happen. It's called a disruption, where you can lose control of the plasma and it can run into the material surface. And it is not great for the reactor as itself. It can damage, but essentially the plasma will break its own confinement. So essentially, once that happens, it kind of automatically shuts itself down, right? So it's not like you can have an uncontrolled reaction that like you can potentially with sort of nuclear fission. So it is sort of inherently safe from that standpoint. It does not mean you actually are using the isotope of hydrogen that we're using to create fusion. Tritium, most notably, is radioactive, and it's usually at a very small amount in the reactor because it actually only exists in the world. There's only about 13 kilograms in the world as a whole, and it is actually, I've been told, and this might be wrong, I've heard that it is the most expensive material in the world. I think it's like multiple millions of dollars per gram or something like that.
So is that an issue for like, what sort of, is that a finite resource then?
It is actually. So the only way so tritium has a half-life of about 13 and a half years. That means that if you had a kilogram of it in 13 and a half years, you're going to have half a kilogram. And then after that, you're going to have a quarter kilogram 13 and a half years after that. So it goes away relatively quickly. Um, that's a problem, though, if you need to like keep it around for running your fusion reactor, right? So um, there's only 13 kilograms. They're typically produced right now in a specific type of nuclear fission reactor that are common in Canada actually. And but there is a plan for a fusion reactor, is that you essentially, one that's based off of deuterium and tritium as its fusion reactor. And you start up the reactor and you create this plasma, and that plasma is creating a lot of fusion, and it's putting out high energy neutrons as one of its byproducts. And what you do is you surround your reactor, your donut, with something called a blanket. And that blanket is made up of lithium. And lithium, whenever it has the ability to have a reaction with a neutron that actually creates tritium. So essentially, you use some of the fusion products, they have to get captured in the blanket, right? Have this reaction in the blanket, which creates tritium. And then you pull the tritium out of the blanket and then put it back into the reactor, right? And so you have to have something that's called a tritium breeding ratio, a TBR, of greater than 1, which means that for every tritium you use, you have to create at least one, yeah, actually slightly more than one actual tritium. There's a whole host of fusion reactions that can occur, and so you need to basically be able to recover every tritium you put in to have a sustaining reactor.
So I'm curious, like, most of us are not a nuclear fusion scientists. And so I think that this conversation has been helpful for me and probably for the people listening to get a better sense of what that life might look like. But yeah, I guess, for you, you're like your day-to-day work. I know you're spending some time with students. It sounds like you spend some time actually engaging with reactors. Like, can you just take us through like how you're spending your time on a day-to-day basis?
Yeah, so I'm sort of an interesting crossroads within our field where I actually do some combination of what some people would consider, theoretical plasma physics, also with experimental plasma physics. I don't really ever think of myself as being a theoretical plasma physicist. I do more computational plasma physics, meaning I run, large simulations, but I also do experiment. And so I've worked on experiments at MIT, out in San Diego, and other places. And so I'm kind of at this crossroads between computational plasma physics, where I'm running these very large simulation codes. I mean, one of the things that I'm maybe most well known for is running some of these very expensive simulations of plasma turbulence that we're trying to understand heat losses from the core of an experiment that I ran. So I ran this experiment during graduate school, took a bunch of measurements, and then I spent something like 100 million CPU hours simulating this plasma and trying to understand how the heat in that particular plasma went from this core to the edge, essentially. And so I spend a lot of my time on computers, and not on my local computer, but actually usually logged into a computer that's in California, where I do really high performance computing. So this is like I can use literally 50,000 CPUs at the same time and run those calculations for 6 months, even on the largest scale. And I'm writing computer code that's essentially analyzing experiments, and then I usually am running these simulations that actually that I can compare the simulation results with the experiment, right? And so I do something called model validation, which is essentially doing a rigorous comparison of a simulation with an experiment. And so what you're trying to do is you're trying to understand, within the uncertainties on your experiment, can you wiggle all the inputs to your simulation, and does it agree or disagree with your experimental measurements, right? And if you do this one time, it's not incredibly impactful, although this is the type of thing we write up. But over the years, we've done this so many times on so many different tokamaks that you kind of get the impression that, okay, our model more often than not is matching the data, right? And so we believe that model now can be used to predict other devices, right? Because we've basically done these comparisons so many times. And I have a really I think, interesting arc within my career, right? Which is that I started out building some things to do measurements on fusion devices. And then I spent time doing validation of these models. This particular model called nonlinear gyrokinetics is the one that I tend to run. And I validated that model over basically a decade. And every time I write a paper, the introduction of my paper always said, the reason we want to validate this model is because we want to use this model to project confidently to future fusion devices, ones that don't exist. And then I think the coolest part of my career so far is that I've actually done that right now. So I did a decade or more of research basically validating this model. We've determined that we are pretty confident that it does a good job describing what we see in the experiments. And now I'm using that model to predict what will happen in all of these fusion reactors, right? And so it's kind of a very fulfilling arc, I think, to see, that we actually kind of moved from basic measurements to sort of high fidelity modeling, validating that modeling, and then finally using it to predict and even design these reactors. So we do predictions that then influence the design of how people are going to build their future fusion devices.
A lot of great words. You guys deal with a lot of great words.
Yeah. So,
Tokamak plasmas.
yeah.
Well, what's fun. We haven't gotten there, but Nathan's wife Anne is in the same field, and so I think about these guys and their dinner table conversations, and
Yeah. To be a fly on
yeah.
the wall.
Yeah, these days there's been a lot of talk of chaotic systems. That's what Anne is writing a paper on and things, and that's actually not even my wheelhouse. But yeah, we do talk about work maybe too much sometimes. I don't know, but it is kind of nice to be able to talk about your work and have your wife understand what you're talking about, right? Like, because I can be really excited about something. I'm like, wow, I just showed that the physics of density peaking in a tokamak, and she could be like, wow, what is it? And then, as opposed to being like, that's nice, honey,
Yeah.
yeah. So, like, it's that is kind of a positive, I'd say.
I think you've really carved out a great spot for yourself, because you have that dynamic where you can like communicate with your most loved one about everything you're working on, and also just like the arc of the technology, as you were describing before, like how you got to be kind of like at the growth of this, like just the pace of technological growth now in many slash all fields are just like such that like things take up, like whereas most of human history was so spread out, you're just like, well, maybe one day, but
Yeah.
probably not. And I think I'll just like pray to a god or something. Like now it's just like all happening like within the span of one human lifetime.
So I actually, there are a lot of guys in our field, or men and women, who spent their whole time, their whole career, right? And fusion has never quite taken off, right? And I'm hoping I'm not going to be one of those people. I'm actually pretty optimistic that we are on the cusp of it kind of taking off here. Um, and so, I'm hoping that by the time I retire, there will be like an electrical producing, fusion power plant, right? And so I'm hoping that's only 10 to 15 years away. I think 10 years is probably a relatively aggressive timeline, but it's hard to actually predict these things. When people kind of poo-poo those timelines, you don't really know how things are going to take off if you demonstrate success, right? Like, if we stay at current funding levels, then it will take a long time, right? But if you demonstrate success and can kind of bootstrap yourself up in terms of investment and people and bringing in really smart people into solving existing, the last problems that exist, you might do this a lot faster than you actually
How much do we actually want to do it is kind of the question. Like, how much does the government actually want to do it, and how much do private companies actually want?
Exactly, right. And so, there have been some massive investments in the field from private fusion company, or so from private entities, right, that are sort of backing fusion companies. Like Commonwealth Fusion Systems raised, almost $2 billion from, venture capital. I think Breakthrough Energy Ventures and a number of different backers. So people understand that there is this need for, alternative energy sources, right? Carbon-free energy, right? And so I think if we can get some momentum, show some real success, I'm optimistic that, we can move things forward quite rapidly, right? To progress towards actual commercial reactors, right?
It strikes me, and I felt this way, like I've known you for a while. I feel very fortunate that we live in a world where people like you are so motivated to like throw yourself at a problem like this because it's something that has the potential to benefit all of us. And I just think it's on behalf of everybody else, thank you for working on this.
Well,
Thank you for your service.
you're welcome. I don't think I'd go that far, but like, it is interesting to me. I mean, it's really an intellectual pursuit that has really an end goal that I find, I want to achieve fusion energy, and the pursuit of it is actually quite intellectually interesting to me. So
Yeah.
that's kind of why I want to go that way, right?
Yeah, the concept behind this podcast, which is called Trail Map, is kind of looking at lives that people build for themselves that are somewhat unconventional and often are like built on, pursuing like going after your interests and like just like doubling down on that. And I think there's something very organic about the process that you described to us about how you came to this space and like made it your own. And so I think there's, some of what Pat described, which is like that serendipity of being in the right place, right time. But I think it's also like you really followed, no pun intended, you really followed the kind of the energy of this space. And I think
You
that
can have
that's
patent
part of
claims, right?
why that's part of why you are where you are. You're like, hey, this is interesting. Other people found it interesting. And so I guess I'm wondering, like, for people that are in school right now who are maybe studying sciences or thinking about studying sciences, and and I know it's a weird time too, just like especially in higher ed. Do you have any thoughts or words of advice for people that are trying to figure out like what path they want to pursue and how they might make an impact?
Yeah, I mean, I wouldn't say that I started out like, knowing that fusion was the thing I wanted to do. I mean, I would say I was just generally interested in science. I actually kind of wanted to go into physics. I wanted to go into astrophysics to start out because I watched the movie Contact, that movie with Jodie Foster.
I was going to reference that earlier when you were talking about the cost of these reactors, and I was like, well, the thing they built in the contact was like $1 trillion or
Oh,
whatever.
yeah,
So
that's right.
whatever.
So, and why build one when you can build two at double the price,
Right.
right?
They broke one.
Yeah, that movie. So I saw that movie. I think I was like in eighth grade, maybe or something around there. And I always loved. I thought black holes were fascinating and things like that. And I read this book by Kip Thorne, who's a professor at Caltech, called Black Holes and Time Warps. And then I'd read some books by these Stephen Hawking's books and things, which are kind of were popular around that time. I started off going to college thinking, hey, I want to go into physics and I'm going to do astrophysics. And somewhere along the way, I'm not sure. I just ran into basically plasma physics as a potentially interesting thing. So I would just, and then kind of, went to internship and as I described earlier, off to college and grad school, et cetera. And so, um, I would say, just follow the things that you're interested in as much as you can. I know that's a little bit easier said than done, right? I mean, I was very fortunate that like I had very supportive parents, right? Like they were helping me go into science programs when I was a kid. They were, encouraging me to do summer. I did summer programs when I was in high school. I did one at Northwestern in Chicago, and I did one in this that was run through Johns Hopkins during the summer. Where I studied physics at this. My friends called it physics camp, but so I was just interested in these things, and they kind of made those opportunities available. But I mean, you don't have to have necessarily access to those things. I mean, I would say, there are a lot of good books that are for popular physics books, like the ones I mentioned earlier. And so just, read about the things that you're most interested in and try to pursue them in school as much as you can. And then just be open to kind of changing as if you think something else is interesting, it's okay to like change your path, right? And kind of pursue something else. And so a good science and math background, if you're interested in going to physics, is really, is kind of is a big deal, right? And but I mean, I would say there's a lot of outreach programs if you're also interested in something very specific, local universities, you can reach out to scientists and professors. I mean, I get tons of inquiries from people all the time and gets similar inquiries and things like that from students. She gave a lecture at I think it was like a high school in Indiana or something like that because one of the students reached out to her and was like, "Hey, we're interested in fusion." She's like, "I'll give a talk at, and
So cool.
so like, oftentimes we're really interested in these. So like people who are really interested in telling people about fusion and or about whatever they're doing, right, within the sciences, you're not gonna have 100% batting or 1,000 batting average, but like, if you reach out to researchers, you'll probably get one that is kind of interested in talking to you, right? And kind of helping nurture your curiosity. And then there's a lot of opportunities as you get a little older for engaging with like undergrads work with us all the time who are interested. There's a program called Europs at MIT specifically, but I did one as undergrad called NUF, and there's one called SULI, which basically do internships in the field of plasma physics. So you can find these types of things. I would say just, try to look out for them. It depends on what age you are, but if you're in college, there are tons of opportunities, and if you reach out to people, you can find labs to work in and things like that. And you might not be doing the most cutting edge thing, but a lot of the Europs and things that I work with end up on papers with us, right? Like you'll be a co-author on a paper and you might be, 19 years old, right? So it's so I would say, I'm not sure that you can just don't say you're stuck to some particular path though. Be flexible to kind of move where you think are interest, because it's better if you're interested in something. Like I don't feel like my job is oftentimes a lot of work. There are definitely parts that I don't love, don't get me wrong, but when I'm doing research, I find that incredibly enjoyable. Like I could do research all the time because I find that to be, it's just it keeps my mind engaged. So the point is, if you find something that really excites you and keeps you interested, then it's a lot easier to spend 8 hours a day doing it, right? So
Are you saying that you just need to create the probability to fuse what you think
yeah, yeah, to give yourself lots of opportunities. Yeah, that's right. But I mean, that is a good way of thinking of it, right? Like, I mean, I was fortunate to be put in a situation where I had a lot of opportunities to try different things, actually, and I was very fortunate from that side. But like you can also put yourselves a lot in, give yourselves more of those opportunities. You just have to be a lot more, putting yourself out there, I guess, because I think there's a lot more that exists than people are aware of, but you just have to look for
Yeah.
them.
Yeah. And I think it does get more challenging in certain ways as you become an adult to dabble in different things and try new things. And so I think it's super cool, Nathan, that you've got the hobbies that you do, whether it's fly fishing or astrophotography, like you're always learning new things in addition to like, deepening the depth of your knowledge on the fusion side. So that's it's cool to see you continuing to learn that way.
Yeah, I mean, in a lot of ways, actually, when I do astrophotography, it reminds me a little bit of some of the experimental physics stuff I do. Like it's very similar, like the debugging and things like that of sort of your equipment. There it is actually very similar to doing that on when you're installing a new diagnostic on a tokamak. There's a lot of similarities there, and so it's kind of been natural, although it's not work at all. So it can be a little less. There's no pressure in kind of dabbling in astrophotography.
All right. Well, Nathan, thank you so much for sharing all of this with us. I think it's been a really awesome conversation, and I'm feeling hopeful at the conclusion of it about the science that you're part of. Yeah. Thank you so much. Really, really, really appreciate you taking the time.
Well, thanks for having me on. This was a lot of fun and nice talking with you and Pat. I'm happy to answer questions if anyone wants to reach out about fusion or something like that.
I
But
have a
yeah,
lot of questions. I might reach out to you.
okay, yeah. So you can find give me my email address and you can send me something.
Great. This was really awesome.
It's great to meet you. I hope I can meet you in person, Nathan.
Thank you, everyone, for listening to that episode with Nathan Howard. That was a pretty cool conversation, and definitely am leaving feeling inspired and thankful that people like Nathan are out there working on big problems.
It's a specific emotion for me. It's like a combination of, as you say, inspired, hopeful, like a little bit intimidated, a little bit like I don't know exactly still what he's doing. And I'm hopeful. You know how he was describing how like in the tokamak they're getting like the temperature of a star in
Yeah,
there.
yeah.
I mean, that seems dangerous to me, but then he seemed like there would be no way that it would go wrong, and I sincerely hope that that is correct.
Yeah, I believe his words were that he would find a new career for himself if we didn't have fusion energy online in 10 to 20 years.
Well, I hope that he can use that ultimatum to shepherd this thing through, and we'll just get rid of fossil fuels and whatnot,
Yeah.
and then also that stars don't explode everywhere.
Yeah. Yeah. And I mean, having said that, like it seems like he'd be pretty happy with a career in fly fishing. So
Right.
maybe that's less of a threat than he
He's
was
got
ready.
he's got options. He's going to be
He's
good.
got options.
Yeah.
Yeah. Yeah. But no, in all seriousness, thanks to Nathan, and thank you very much, Pat, for joining the conversation. And it's really a lot here to chew on. And I think like one of the biggest takeaways for me was just like, how Nathan has followed his passion for fusion and for finding a resolution to energy resiliency for the future. And I think that that's like a pretty inspiring um, and very human path.
Yeah, I agree. It's also great that he and his wife are in the same field. I feel like
Yeah,
that's great. When you can swing it, that's a great scenario.
totally. And she's a wonderful human being, just as he is. So
Yeah.
feel very grateful to have them both in our lives. But yeah, anyway, thank you again, Pat, and hope we'll
Thanks
have
for
you on
having
a
me.
future episode very soon.
Yeah, let's do it.
All right.
I
See ya.
said that at the beginning too. Let's do it.
Okay. Let's do it. Bye bye.
Bye.